Well, guys, good day once again. Hey, we're going to talk before we start to talk about some of your practice problems and in our end of the year review. I thought I'd bring your attention to a couple of things I hopefully you've already found in the Canvas page. But anyway, if you haven't, I want to draw your attention to them now. One of them is about a 6-page document here. We call it Stuff You Must Know Cold. Now, it's really just a nice extended reference sheet with some very nicely organized information, things we've covered throughout the year, even some pre-calc things like some trig identities and some graphs and things like that. But I really want, hopefully, as you're working through the practice and the review the next couple of weeks, you'll familiarize yourselves with some of the things on here again, some of the things we haven't seen in a while. But I really do want to encourage you to use the next couple of weeks to familiarize yourself with things on here. I really would think that even though this exam this year is going to be taken at home, and every student in the country really is going to have free reign of whatever resources they might have. This is a nice one, but I really think you don't want to rely on it too much. In that, if you're spending 5-6 minutes of your time limit looking up something on the sheet, you're probably not using time wisely. So I just want to, hopefully this is a good place to just have a nice organized bit of information for you as you're doing your studying and reviewing. Okay. The second is an article written about the AP Calculus exam. Well, it's just called how to not just survive but thrive and or prevail. And you know this is written by a gentleman who I believe used to be one of the lead test readers and test writers for the College Board. And so, very good wealth of information here. I know it's a long article, and a lot of it at the beginning, especially, does not apply this year. But I would draw your attention to page 5, information starting at the bottom of page 5 and on, where he talks about free response problems and some do's and don'ts, quite a long list, and some just suggestions for increasing and maximizing your score potential on the free response questions. Um, I think I mentioned during the year when we were together that last summer I was an AP exam reader, and I can vouch for most of what he's saying here that it's true. How the students' work is read and scored is very much in agreement with what he's saying here, guys. So I'm going to be talking through a lot of those things as I share solutions to problems the next few weeks here. Okay. Also in the article, he mentions things you can and can't do with your graphing calculator and on the free response questions. And so I'm also going to be for sure talking through and demonstrating a lot of that, even on the question we're going to talk through today. That being said, I'm going to go and bring up the problems that you've been working on since Wednesday, and I'm going to talk through question 3, so you can kind of see how it would be ideally solved, and then maybe this will give you some help and suggestions for working on problems 1 and 2. As you'll notice, there's quite a few similarities between the problems here, and this is a classic rate in, I call it rate in, rate out kind of a problem, as that's what's happening here. The only thing that they've changed a lot in the different problems is just basically the scenario they're describing in the words. Okay, so this one happens to be about rain flowing in and out of a drain pipe. And so as we read the problem here, the rate of which water flows into a drain pipe is modeled by the function r. And so right away they've defined an equation this time for the function r. Now, again, the way sometimes the presentation might be different, like maybe instead of an equation they give you a graph, or maybe instead of either of those they give you a table. So in this problem, everything's given as an equation. They're defining the units of this function coming right after that. The value of r is in cubic feet per hour. Okay, so it is a rate. The time in this function is measured in hours, and the domain for this is the times range from 0 to 8 hours. Now let's continue. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by, now here's another rate, and here's the expression for it. Also measuring cubic feet per hour for the same domain, 0 to 8 hours. And then it states that there are initially 30 cubic feet of water in the pipe at t equals 0. Again, important information. Just because it's at the end doesn't mean we ignore it, okay? And first thing to realize, not everything in the paragraph is going to be needed for every part of the problem. Maybe sometimes some little detail in this paragraph might only be needed for one of the parts, okay? So just let that be known ahead of time. Now, the first thing I suggest is if they give you equations, don't start any work until you've put both of them into your any of them into your graphing calculator. And so I'm going to bring my calculator up here, and I've already done this ahead of time, I think. Yes, so I have function R as y1, function D as y2, and another very important thing to check, function R involves a trig function, the sine function. So before we do anything, let's make sure our calculators are in radian mode. See, mine wasn't, so we're going to make sure it is. And so now we should be ready to start. So let's read part A. Part A asks, how many cubic feet of rainwater flow into the pipe during the 8 hours, 0 to 8, time between 0 and 8? First, let's make a note. This is only about the flow into the pipe. And so this should only involve function R, where it is the rate of water flowing into the pipe. Okay? Now, one very important notion we learned back in the topic of integration was something we called the net change theorem. And basically, in plain words, it says the integral of a rate of change gives the net change. So in this case, I have a rate in cubic feet per hour. I would like to know how many cubic feet flowed into the pipe. So this is a very quick calculation computed by an integral. It'll be the rate R integrated over these 8 hours. Notice that in my work, I'm not even going to rewrite the expression for R. It's not required you do that if the function is named in the problem as function R. You can just name it in your work. Second, this is a calculator permitted question. That means there is no point awarded for providing things like the antiderivative or anything. In fact, I can tell by looking at this one, this is not one we actually know how to integrate, because even though it is a composite function, something inside of the sine function, a u substitution isn't going to work because the derivative of t squared is 2t, and I don't have a t outside of the sine function anywhere to be the du, right? So we couldn't find the antiderivative of this even if we wanted to. You're not expected to. This is strictly a calculator question. So all we're going to do is use the calculator's integration tool, and we've used this many times, but we go alpha window 4. It brings up the integration template. We're going to type it in just the way I wrote it, 0 to 8. And if you, instead of typing in the expression, remember you can just use alpha trace, and then we're doing y1. And in the calculator, the variable is x, so we're going to just go dx. And this is all it takes. Okay, and so I've got the answer 76.570. The rules for rounding on the AP exam, as I've been telling you all year, is unless they tell you otherwise, 3 decimal places. So after the 5 and the 7 is a 0, and it actually does not matter whether even though this naturally rounds down anyway. So the only correct answer they're going to allow here is 76.570. And one more comment here, the units are not required to be on the answer because they were given to you in the question. it's told you that the answer needs to be in cubic feet. So you do not need to label this. You will not lose a point if you don't label it. So the only thing you get a point for here is the integral, and then the answer 76.570. One quick comment here, even though it is a zero, you have to have it. If you just put 0.57, you'll lose a point there. Okay. B asks, is the amount of water increasing or decreasing at time 3? And we have to give a reason. Okay. Now my thought process here is there's two rates working. There's the rate at which the water goes in, and if that was the only one that was, if water was only going in, of course the water level will be rising. There's also another rate, the rate at which water flows out, and if that was the only one that was at play here, the water level would be decreasing. But this time there's two rates working. So my thought process really is if the rate at which the water enters the pipe is bigger than the rate flowing out, then the level would be increasing, and the vice versa for decreasing. So all I really am going to do is compare the two rates. So the rate of R at 3 and the rate D at 3. And again, this can entirely be done on the calculator. You do not need to do the finer parts of the arithmetic here. Okay, so on our calculator, we'll go back to the home screen. We can go alpha trace y1 of 3, and it's 5.086. And we'll now do the rate out. And we'll evaluate it at the 3, and I've got 5.4. Okay, now it's exactly 5.4, so we can leave it there. Now, all I've got to do is put some kind of an explanation. Now, they're going to want to see that you did some calculation here, even just providing this, and then it says give a reason. So I'm noted, my observation is the rate of the water leaving the pipe is bigger than the rate entering the pipe. So my conclusion is going to be that the water level is increasing. And so, we're going to write a complete sentence here. The amount of water is increasing because the water, we could even just say that is entering oh, you know what? I'm miswriting it here, guys. Sorry about that. We want to say decreasing because the water is entering at a slower rate than it is draining. And it's not a bad idea to put the time here again, so draining, and we say when t equals 3. I think that would be the ideal answer here. We mentioned the time again, 3 hours, and we mentioned how we're using the information over here, okay? So for example, if all you have is something like, I know the water level is decreasing, but don't put a reason, when I show you the rubric here, you'll see that you would not earn a point for that. You have to have a reason stated, okay? So something like how you're using the comparison here, okay? An alternate way to say this would be to do this. The overall net rate of change would be this: the rate at which you go in subtracted by the rate at which you go out. And in this case, this is 5.086 minus 5.4, and that is less than 0. So if you think about the difference, the rate in minus the rate out, would be the overall net rate of change of the water. And if that rate of change is negative, then the thing that's changing, which is the water level, is going to be decreasing, right? So that's another way to make your comparison, just to construct the overall rate of change and observe that it would be negative. Okay, and then a negative rate of change indicates that something is decreasing. Okay, let's point out something right now. This is mentioned in the article that I asked you to read. That is, you notice how little arithmetic and even a little bit of writing we're doing here. He mentions that if you find in many of the free response problems, if you find yourself doing a lot of extra and tedious algebra and things, you're probably not doing it the way they intended. You're probably doing the problem wrong at all. Okay, so notice how brief some of the solutions are and just how concise it is. It really can be that simple. If you know what's needed to solve the problem, your answer and your presentation does not have to be very elaborate. Okay. Let's move on to part C now. And it says, at what time between the times 0 to 8 is the amount of water in the pipe at a minimum? Okay, well, this reminds me of when we solved max-min problems. One type was when we had to maximize or minimize something when we were studying the function on a closed interval, and that's what this is. There's a closed interval. It's between 0 and 8 hours. So it reminds me of what we call the candidates test. We need to narrow this domain down to a series of candidates, and the maximum, or in this case, the minimum, will have to occur at one of those candidates. Remember, the immediate candidates are the endpoints. So right away, we're going to identify candidates. Okay, and t equals 0 and t equals 8 are automatically candidates. They're the endpoints of the interval. Okay, so for example, if the water level was decreasing the entire 8 hours, remember we found that it was decreasing at the time 3 hours just a minute ago, but if it happened to be decreasing the entire time, then the minimum would be at the end, right, at 8. The opposite would be true if we were to somehow establish that that the water level increased the entire time. The minimum would be at the beginning, right? Now I have a feeling that's not happening here, but we have to list them as candidates. Now the other candidates would be when the water level changes from increasing to decreasing, and that would happen at any moments when the rates of in and out were to change position relative to each other. So in other words, if during the first time if during the beginning maybe the rate in was bigger than the rate out and the water level was increasing, and then there came a time when they were equal, and after that the rate out was bigger than the rate in, the water level started to decrease, and they might crisscross a couple times. Okay, so any time that the two rates are equal would have to become a candidate. Okay, so we need to solve an equation here to find other candidates. Now, this would be one way to state it, or remember we introduced the expression of the overall rate of change in the previous problem. You could think of this as the overall rate of change. And we'd be just setting that equal to 0. I hope you notice that these two equations are equivalent here. Okay, so if the two rates are equal, that's equivalent to saying the rate in minus the rate out would equal 0. And so if you think about that now, that's setting you can think of it as we're setting a derivative or a rate equal to 0, so we're finding the critical numbers. Okay, so again, a job for the calculator. This time we need to produce, the best way is to use the graphs. And I did not set my window up ahead of time here, so I'm going to go and set my window now 0 to 8. And I don't know how big this needs to be. I'm going to try it here and see how it looks. Okay, I see they did crisscross once, but I don't know that they don't do it again, so I'm going to make this window a little bit bigger. Okay, now I've got it, and I see there is only one intersection point. So we're going to just get the calculator to find it. And so that's under second calc intersect, another tool you are perfectly allowed to use. And we've got it there, 3.272. Okay, and so that becomes one of the candidates. Okay, now the question is, at what amount of, when is the amount of water a minimum? Well, usually when we're using what's called the candidates test, what we do is we find the candidates and then we plug those back into our function. Well, the function that we're trying to maximize is the calculation of the amount of water. So what we really need to do is formulate how we actually do that. So let's think about that here. How would we actually find the amount of water in the pipe? Okay. Well, we found how much water entered the pipe in part A during a certain time interval. So an integral does that. And so if I were to repeat that again and find out how much water entered the pipe, maybe during other time intervals, I could use integrals again. If I want to know how much water left the pipe during any time interval, I would use an integral of d. But now let's not forget that there were 30 cubic feet in the pipe at the beginning. So I believe we could even just make up a name here, like W for water. Okay, the water in the pipe at time t. Well, at zero hours, there was already 30 cubic feet in there. And then I would add back any water that entered the pipe up to a certain time. Okay. And now you notice we're going to have to change the variable in R now to something else for a little bit. So, changing it to R of X is perfectly fine because now the T is the upper limit of the integral. Now we want to subtract any water that exited the pipe during that same time interval. Okay, and this would now be d of x. So really, to finish the candidates test, what we're going to have to do is find w of 0, which we already know is going to be 30. Okay, that's the amount of water at the beginning. We now need to find how much water was there at the first critical number, or the only critical number, 3.272. And then we need to find the amount of water at the end of the 8 hours. Okay, now once again, these last two you're expected just to do this with your calculator, okay? So what I'm going to do is go back to my calculator and set this up as to define the critical number, 30 plus, and set up my first integral. This time it'll be 0 to the 3.272, and the input rate is y1. And we're going to subtract the 1 for the output rate. This is y2. And it gives me 27.964. And it actually rounds up to 965. It actually does not matter, by the way. If you forget to round up, they don't care as long as you have that third digit there. Okay. And then we'll go and we can repeat this now. What I'm going to do is use that shortcut here, second, enter, and I can go back and just edit the upper limit of the two integrals. Okay, so I'm just going to go back here and change them to 8. And repeat this. I got 48.5436. So we'll call that 48.544. And remember, we were asking for the minimum. And so it looks like all we got to do is look at the list and see which one had the least amount of water. It is this one. Okay. So the conclusion is at what time? The answer is a time. So the minimum amount of water was at the time t equals, and we put the time 3.272. That's all you have to have. The justification is your listing of the candidates and performing of the candidates test. Okay. So notice again, we're not doing a lot of super complicated arithmetic, but we did have to know what the arithmetic to do was. Okay, all the actual number crunching was done by the calculator, and then we had to do the explaining. Okay. Okay, we're almost done. Let's go to part D. This is a short one. So part D, the pipe can hold 50 cubic feet of water before overflowing. For T is greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. Now, this kind of reminds me of something in the article that you were going to read, and it is things like sometimes parts that you do in previous work you do in prior parts might give you some suggestions about how you're going to solve this one. And to me, something we did in part C definitely gets me ready to do part D here. It's asking about, we need to solve an equation for when the overall amount of water is equal to 50. Okay, so in part C, remember we constructed this expression for the amount of water at any given time, 30 plus the integral from 0, we used t in the previous one, and then we had like r of x. Now in this one, both integrals are going to be for the same interval, and in fact I could have done this last time too, so we could put them both in the integrand and not have to have two different integrals. Okay, but notice the parentheses, notice the dx. Okay, basically we want this to equal 50, right? Now, the only thing I'm going to have to correct here is they want our variable to be W. Okay, so we're going to go back and say, okay, we basically want to know when will the total, at what time will the total amount be 50? So we want the variable, the unknown number is at what time it is, or the upper limit of the integral. So that's where the W needs to go. And actually, so when I see that, the variable in the two functions really could have been just back to T again. Okay, so not that mine's wrong. But if you want to just use t, that's perfectly fine because w is the variable up here this time. And this is all you would have to have. Again, no complicated arithmetic. This is your equation. Okay, now you could adjust this a little bit. Equivalent ones would be maybe you just want to take this integral instead of equal to 20 because you could subtract the 30 away, and as you're saying, well, there was 30 in there at the beginning, so you want the net change over that given time interval to be 20. You want to add a net of 20 more, right? That would be fine too. But this is the way I'm going to write it here. So if you want to hang on with me, I know we've got a bit of a long video going today, but let's just take a look at the official scoring guide for this question. I think this is an important thing for you guys to see as we go through some of the problems here. Exactly how do they award points, and what exactly are they looking for? Okay, so I have that ready to go. Now remember, every free response problem, no matter how many parts there are, is always going to be a total of 9 points. I don't expect that to be any different this year. And so here's the scoring rubric that was used for this problem. Again, notice kind of how brief it is. Here was our work from A. Again, this was a very short setup here, and they're doing the exact same thing I did. And this was 2 of the 9 points. So 1 point for integral where the integrand is r, and then 1 point for the correct answer, 76.570. Okay. Part B was also worth 2 points. Remember, we had to figure out if the water level was increasing or decreasing. So you earned the first point if you consider both the input rate and output rate at the time 3 hours, regardless of what you did with them. Okay, so as long as you have noted that you're going to use both those rates to get to your conclusion. And then 1 point for the answer and the reason. So I want to point out that's all 1 point. So if you put things like the level is decreasing but don't give a reason why, you're not going to get that point, because really otherwise they could just assume you guessed. Okay, so you have to have a valid mathematical reason. In my explanation, I put that the rate going out was bigger than the rate going in. Okay, and that's kind of what they have saying here too. Okay. C, here was in their work over here is most of what I was trying to do. They're spelling out the candidates test by first explaining how you calculate the amount of water in the pipe. Okay. Now if you think about it, what they've got written here is really that function, that expression's derivative, and they're setting it equal to 0. And now what I did was I set the rate in equal to the rate out, and we used the intersect tool on the calculator. So that is perfectly fine, and they do have that candidate there. Okay. Now they're also equal at the beginning, but that would have been a candidate anyway because it's the first endpoint of the interval. And here's the table of information, the 3 candidates here and the 3 amounts of water, and clearly this one is the smallest. Okay, so this one earns 3 points. The first point for considering this equation, or the equivalent one that we were using when the rate in equals the rate out. So I think those would be okay too. When R of t equals D of t is an equivalent equation. 1 point for the answer. What they mean by the answer is the time, okay, 3.272. And then 1 point for the justification. The justification really is the fact that you considered all of the candidates, not just the critical point, but the 2 endpoints also to rule them out. Okay. And then D is again just worth 2 points. One, if you have an equation at all, okay, or if you have an equation, if you have a complete equation, it's 1 point. If your equation contains this integral, that's the second point. Okay. So just want to hope that helps you today. I think questions 1 and 2 that you're working on and are going to turn in have some very similar characteristics to them and some very similar lines of questioning. And I hope if you watch this video all the way through today, that's going to help you with some of those and hopefully others. Okay. And we'll have a great day. We'll talk to you again on Monday.